Hello, 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 Michelle F. Hello, good afternoon, Shy. Hello, Paulina H. Hello, Stephanie I. Hello, Maria Z, who's been in the room since 2000 BC or something, which I appreciate. Hello, Yavi, who is totally, hello, Alan, who is both are very three-dimensional. That makes a total of Oh, are they doing that thing again? Thank you, Alan. I just caught that. Thank you. That just made my day. Okay, I'll keep. Um, and there's Chris. Oh, I think they're doing that thing. Okay, which is cool. All right, I'm gonna stop. We're gonna do work. But hello, everybody. Well, okay, wait. No, I'll do the chat. No, people saying hello. It's very important to say hello. Good afternoon, Shy. I said good afternoon, Jada. Good afternoon, Michelle Q. Good afternoon, Marilyn C. Good or Che. Anyway, good afternoon, Michelle F. Good afternoon, Katie. Good afternoon, Alan. The worst thing I do with this, all these hellos is like I say hello and then I bump on someone's name and then everybody's like, what's he think? Okay, anyway, good afternoon, Emily, but it's not good afternoon, Paulina. Good afternoon, Maria. I like how Maria like stays away from any kind of judgmental. If she's like, I'm admitting it's an afternoon. That's as far as I'm going with this. Right. Okay. Good afternoon. It's very scientific, actually. Good afternoon, Yavi. Good afternoon, Allison. More people coming in. Good. Hello. I still have the chef status. I'll take it. Thank you. I feel like the Swedish chef on the Muppets, but I'll take it. Thank you. Um, oh, you're saying I'm built like oh, what's the guy that I used to in my marriage? Oh my God, the guy from Long Island. Oh my God, the guy that every husband is jealous of. I can't remember. Not the diners, drives, and whatever guy is not. I'm not jealous of him, but yeah, no, yeah, not Gordon Ramsay. I mean, he too. No, oh my God, he's got this gorgeous house on Long Island. He's like always cooking brunch for his like gorgeous wife, and he's all like fit and everything. Oh, everybody knows who I'm talking. Oh my God. And it's I'll think of it in a minute. But hello, Shawnee. Okay. This is okay. Hello. I should get to but hello everybody. Oh, and Cheska, who's doing interesting things. Okay, I won't get involved in that. Okay. Oh, it's just a yes. Okay. Whoever said Cheska didn't give a fork. Just kidding. Okay, it's totally rude. Okay. What? She's like, wait, what did he just say? Okay. No, all right, let's get going. The person I'm thinking of, Bobby Flay. Bobby Flay is who I'm thinking of. Okay. Is that his name? His actual last name is like an actual cooking term? That can't even be right. Okay, no, we're gonna do physics right now. We're gonna go back to, and there's Fariel. It is, believe it or not. Okay, so at least that is his name. Okay, that's just too crazy. That's like if Yaverbaum were a physics term, which would be problematic. Okay, let's go to physics. One thing though, today is no, yeah, let's do physics. We're gonna go back to homework 2. I'm trying to make tracks them even since I'm all something right now. It is, believe it or not. Okay, executive chef. Okay, head chef. Oh, and now Alan. See, I want to get to physics, but see, once Alan gets involved in the game, then it's like a whole higher level game. Like not to be, but then I like have to take it seriously. Okay, anyway, um, Alan got demoted. Whoa, because he's not video anymore. Oh no, he's back. No, okay. He messed up in lab. Ooh, that sounds like a. Okay, I'm not going there, but noted, but not, but yes, but not. Interesting. Wait, when is your? Okay, no, I really see you guys are. Okay, that's funny. Okay, okay. I want to go to physics. One weird thing though that someone pointed out to me. Wait, no, we're gonna go back to homework 2. I'm gonna try to plow through that. There's like different types of exercises in homework 2. I'm gonna try. Oh, Logger Pro. Yeah, fair enough. I wouldn't take it. Logger Pro is, yeah. You have my sympathy. So I'm gonna go back to homework 2. I might even show the screen to say we're going back to homework 2. I'm gonna try to go faster and just like say things, and I'm gonna try not to over explain them because I know that's like an issue. But the more people want me to not over explain things, the more it'd be better for me to just like say things. That's great. But then the more it's on you guys to really stop me when you have a question on, okay, for whatever it's worth. I'm not saying there's been complaints, right? I, yeah, I'd probably be better for everybody if I anticipate questions less and just answer them more, if that makes sense. So, and if it doesn't, put that in the chat. But so we're going to go back to homework 2. Yeah, like right now, I'm just looking in the chat. Oh, no, Logger Pro definitely has haters. I can't even joke about it. Yeah, no, for real. I mean, Logger Pro is like, uh, uh, I mean, it's necessary. It's like the best option there is, but it's not a great option. Okay, wait, one thing, see you, yeah, no, I know. Logger Pro is like old and creaky. The one thing I want to say about Logger, and the whole reason we use it, okay, this is like vaguely physics. I know. It's like a drag to use, especially in this day and age when we all could do better with stuff like that. The one thing about Logger Pro, the main reason we use it is exactly what you're mentioning in the chat. Like it is for analyzing data. No, it's actually, well, it's for taking data that you collect with some instrument and then putting it into the computer so that you can then analyze it properly, right? I mean, I know you know that, but the main thing of Logger Pro is just an interface. The main way you should use it is as an interface between pieces of hardware that, collect data like motion sensors or et cetera, between those pieces of hardware and tables of data that the Logger Pro creates. But honestly, one thing is, and yes, that means, for example, importing videos into Logger Pro and then putting the red dots in there. And by the way, if you guys are talking about Logger Pro, right? Okay, I really do want to get to the homework, but if what you're talking about is using Logger Pro in lab 3 or whatever, lab 3, the creation of a wave, that business, if that's what you're talking about, I will stop on what, maybe just let me know in the chat. If that is what you are talking about, yes, that is like a big, sort of scary, intimidating, weird thing at first, but it is big and important. It is definitely one of these labs where at first it's like, there's so many levels at which we all don't know what's going on. I understand that, but it really is not busy work. Like, we come back to lab 3 a lot in the rest of the course. It's understood to be confusing at first, but you do have to stick with it and stick with me in analyzing it. So be patient with yourselves and with it. It doesn't come immediately to everybody or to most people, but it is worth it to stick with it. And if that's what you guys are talking about, I will stop and be more careful and helpful on Wednesday, unless you literally tell me in the chat that you have a report due Wednesday, then I'll stop what I'm doing right now and I'll shift gears. I will. But unless you have a report or something due Wednesday, I will make a big point of talking Wednesday about it. It's just, it'll be easier if we get through a little bit more material here. And I'm happy. Remember, this is a place. It's not off the topic. It's not a joke. If you have issues from lab that you want to bring here and have me straighten out, that's what should happen. I mean, that is what I'm here for. And the whole thing should be together. So I will do that Wednesday unless you tell me in the chat, and I will look in a second. If you tell me in the chat that you have something due Wednesday, I'll do it right now. But other than that, I will do it this Wednesday, in 2 days. And the one thing I'll say for the moment about Logger Pro is, one thing is, yes, you're using Logger Pro correctly. It's the least of all evil worlds if you use it to like import a video and put red dots in that video. I'm not saying that's fun, but yes, that's a use of Logger Pro for which there really is no substitute. But once you've done that, let me absolutely reinforce or remind you that then ditch the Logger Pro. Do not use Logger Pro to create graphs. I know it seems like it can, but it's terrible at it and it's misleading. What you want to do is just get tables of values from Logger Pro and then use those tables of values to go over to ideally Desmos, but if you can't handle Desmos, then Excel or something like that. But okay, that's my little speech for the moment. But Logger Pro is basically for the red dots. That's the purpose. And if you're using it for any more, then you're definitely making your life more hard than it should be. All right, I'm going to look in the. Yeah, no, I totally understand. Worst code. Yes, it has. Okay. I should. No, yeah, and the red pixels are. You are. Okay. Okay, and thank you, all of you. Fair enough, and thank you, Katie, for what you just clarified. So listen, and you can remind me, all of you, it's an important enough lab, and it's hard enough. It is definitely one of those labs that makes no sense at first or seems annoying at first, but it ends up meaning a lot. So the more I can talk about it while you're doing it, fine. And that analysis gets into derivatives and differentials, like differential equations. It's all related. I promise it's not arbitrary. But yes, then if you don't have something to do, if you're doing the analysis on Thursday, Wednesday will be a perfect day. Please remind me if I don't remember. Okay, at the beginning of class. Like, I'm serious. Like, I'm glad this just came up, even if it came up as a joke. That's kind of why I like your jokes, I guess. Okay, but it'll all make more sense if we do a little math first. So I'm going to go back to the homework now to to homework 2. I think the big conclusion that we just got, so we're homework 2. Sorry. I'm just pulling it up. We just did, all right. The one we just did, I'm just pulling it up. Yeah, the one we just did last Wednesday was like F and G was 1 F and G. We already did them, but I'm just going to remind us of the finding or the result. F and G was if X equals a cosine omega t plus 3.5, we said, then indeed that potential possible, that function, omega t plus 3.5, that function, if you differentiate it twice, you do get the differential equation for simple harmonic oscillation, which is the whole key to all this stuff that we're doing. So what we concluded from that, like basically I'm saying, like, even if you stick that 3.5 in, you still have a harmonic oscillator. And what we said on Wednesday was the 3.5 itself is not a special number. It's not about the number. It's about the fact that it is a constant number. So we said from now on, you can stick any positive or negative number in that cosine argument, and it still will describe, it still will satisfy that differential equation. So it still will describe a simple harmonic oscillator. Hold on, I'm all over the, okay, yeah. So we're now saying, let's just give a name to that number that can be stuck in. We're going to be saying, all right, I'll put it on the next page. We're saying, I don't care whether they're talking about X or Y or whatever, if we're talking about any general dependent variable Z, if we have the differential equation, if this differential equation describes a dependent variable Z, then Z is a harmonic oscillator. That's what we're saying. Or the value of Z oscillates harmonically in time according to this cosine solution that we've been working with. Now what we're saying from here on in is the cosine solution is actually more general than we believed before. Before we assumed that we didn't think there was a symbol there at all in the argument. Secretly, what we were assuming without realizing it was that the symbol was there, but that its value was 0. Now we're saying its value doesn't have to be 0. It could be any positive or negative constant. So what we're saying now, like we're just saying mathematically, that seems to work. So physically, we're saying from now on, that constant that can be put in there, we're going to call the phase constant. We're saying it's a number whose units must necessarily always be radians, right? Because otherwise you couldn't add it to omega t and take the cosine of the total. So it's some kind of number measured in radians. And what we're saying is it's a number of radians that measures or signifies a head start or a delay in the oscillator, but with regard to cycle, to portions of a cycle. Because again, technically what I'm saying right now is like review of where we left off on Wednesday, head start or delay in portion of cycle, right? Because remember, the key to all of this that I believe I hope I clarified like 2 classes ago. The key to all of this is now we're thinking trigonometrically, we're thinking in what seem to be angles, and we're thinking in radians, really because a radian, well, because an angle is a fraction of a circle. When you measure angles in radians, you're measuring the size of a fraction of a circle. And a radian is just the most direct way to do that. So for example, so the whole thing hinges on the fact that 2 pi radians is a full circle, and pi radians is a half circle, and pi over 2 radians is a quarter circle, etc. 2 pi radians, because the circumference of any circle is 2 pi r, 2 pi times its radius. A full circle, the angle that constitutes a full circle, is 2 pi radians. And that is true no matter how big the circle is. That's the whole point, is that no matter how big the radius of a circle is, the ratio of arc length to radius that you get for going around the entire circle is always 2 pi. Like if the radius is twice as big, you get twice as much of a circumference, right? So that ratio between circumference and radius is the same no matter how big the circle is. And that ratio, the ratio between the arc length that you walk versus the radius that you walked out, that ratio is what we really mean by angle, right? Okay, again, this is all just review, but the key takeaway is that there's two. Oh, okay. Sorry. The key, like conversion or anchor to all of this, how we're going, why it is, how it is that we're talking about circles and angles and trigonometry and cosines when we're looking at something that's just going back and forth in a straight line, right? The whole key is that we are taking what is true universally of circles of any size, and we're grafting that mathematics on what is true physically about cycles of any size, right? One cycle from here on in means 2 pi radians, or the other way around, like 2 pi radians means one cycle from now on. So from now on, what 1 radian is approximately a 2 pith of a cycle, or in other words, well, I mean, it's exactly 2 pith of a cycle, so it's approximately 1/6 of a cycle. Like literally, I'm going to say that again because it sounds just approximate enough to seem off the top. The key from here on in, whenever you hear radian, think 1/6 of a cycle. That's what we're saying. All right, it's not exact, but it is. But the concept is exactly right. The number is just not exact. But so a radian equals a 1/6 of a cycle. Therefore, this phi number, this phi, the phase constant, is a measurement of how ahead or behind in the cycle the oscillator is when you start your stopwatch. And so really, more realistically, more experimentally, the better way to think about the phase constant really is, at what point in the cycle did you decide to start your stopwatch, right? Okay, everything I'm saying right now, again, I mean, technically is review, and even though I'm talking fast, I'm trying to actually just expand the last things we said at the last class. So technically, this is all still, I'm just explaining what we took away from that last part, Roman numeral 1, parts F and G, okay? And then I'm going to move on to the next problem, I promise. But this is a big takeaway, and you need to understand this for the whole wave lab. This is the transition to waves, for whatever it's worth. So what I'm saying is, B signifies the point in the cycle at which we started our stopwatch, like literally, at which we started the experiment, started collecting data, started paying attention. Our stopwatch, i.e., where in the cycle is what we're calling t equals 0. I'm going to do a quick example of this right now. Again, this is an example to demonstrate the point. It's not a problem from the homework. You call it a sidebar or whatever. This is an example of how phi works, because from now on, it's a general takeaway. This phi is like in all of our understanding from now on. So I'm saying example. If we analyze the mass in the spring from now on with x equals a, or not even a, let's call it x naught, sorry. Either one is, but if we say from now on that describing a mass on a going back and forth on an x-axis on a spring is x equals x naught cosine omega t plus phi, which is what I'm saying from now on, what that means is if phi equals 0, as it used to be without us realizing it, if phi is 0, if that constant equals nothing, then the meaning of that is then when t equals 0, right? Like if phi is 0, that means we start our stopwatch when? Well, it means we start our stopwatch exactly what we expected and did with the most natural thing. It means when phi is 0, then x, that with phi is 0 and t equals 0, then that means when t equals 0, x equals x naught cosine of 0 plus 0, which is to say x naught cosine of 0, which is just, and the cosine of 0 is 1, because the sine of 0 is 0. So the cosine of 0 is 1, right? So, so I'm saying so far, it looks like I'm saying something that's not new. That's correct. I'm saying when we didn't even know about phi, when we just tacitly set phi to be equal to 0, that meant we were tacitly assuming that we started our stopwatch in the most natural place. We started our stopwatch at the beginning of the cycle when we started our stopwatch when the mass was at the amplitude position, when it was all the way out as far away as possible from equilibrium, right? That's like the most natural, sort of convenient, easy way to do the experiment. And that's what we did. And when you do the experiment that way, that means phi, there is no phase delay or phase head start. You're starting the watch and the experiment at the beginning of the cycle. But if someone were to say for that same exact experiment, but if phi, let's say, equals, let's say, pi over 2 radians, that's a perfectly reasonable and common, meaningful thing that phi could be equal to. In other words, if the equation that we're saying for that oscillator is x equals x naught cosine omega t plus pi over 2, then what that means is then when t equals 0, I'm just plugging in. If t equals 0, but phi equals pi over 2, then then x equals x naught cosine of 0 plus pi over 2, right? Which means x equals x naught cosine of pi over 2. And cosine of pi over 2, and I should stop and say, if we say, well, no, I'll just finish the thought. Cosine of pi over 2 means cosine of 90 degrees, right? Like on the unit circle. More to the point, really, what does pi over 2 radians mean? It means a quarter of the circle, right? 2 pi always go back to this. 2 pi radians is all around the circle because the circumference of a circle is 2 pi r. So 2 pi radians is the whole circle. Pi radians is half the circle. Pi over 2 radians is a quarter of a circle. If you're picturing the unit circle, that means going, from the edge up to the top. So the cosine of pi over 2 radians is 0, right? So that means if we if we didn't start our stopwatch at the beginning of the cycle, if we started our stopwatch, what it means is that if you set phi equal to pi over 2, it means we started our stopwatch a quarter of the way into the cycle. A quarter cycle in, i.e., when the mass is not at the amplitude position, but at equilibrium, right? Bottom line, pi over 2 means quarter cycle, because again, a cycle is not pi, a cycle is 2 pi, right? So pi over 2 means a quarter of a cycle. So if phi is pi over 2, that means there was a quarter cycle delay or head start in the timing. So it means when you started your stopwatch, the mass was not at the edge of the cycling, it was at the middle. If phi had been pi, then it would mean that the mass was on the other side, etc. Okay, so that's what it means. So phi is a measurement of delay or head start. Okay, a very good question. I mean, a very important question is, like, why do we, if phi is, why do we do this? Like, why do we care? I mean, if phi is measuring where we started our stopwatch, and if we all agree, which, I do feel that the most convenient, natural place to start your stopwatch is at the edge of a cycle. And if indeed we can start our stopwatch whenever we want, the whole point of physics always comes back to Galileo's principle of relativity. It always comes back to there's different perspectives from which to look at something. There's different coordinate systems. You can set your coordinate system for data collection in more than one way, always in physics. So the whole point is you set it the way that's the most convenient. Why would we ever not start our stopwatch right at the beginning of the cycle? It's a very good question. And here's the answer that will bring you back to lab 3 and bring you back, like you'll see, this all relates to lab 3 and that topic eventually. You wouldn't. If you only have one oscillator, you always would just do the most convenient thing possible and start your stopwatch at the edge of a cycle. And if you only have one oscillator, you'll always end up setting phi, pretty much always end up setting phi to 0, which is why we got away for the first month of this curriculum not caring about phi, because you often don't have to care about it. The reason that phi would ever come up oops, sorry. The reason I'm making a big deal about phi, the reason we care about phi is if you have more than one oscillator oscillating at the same time, especially if you have many, many oscillators, and they're all like identical in parameters, like they're all the same K, they're all the same M, whatever, they're all the same omega. But if you have a bunch of oscillators that are staggered, that are not all starting at the same place in their cycle, then for one of them, you can start your stopwatch when it's at the edge of the cycle, but necessarily then your stopwatch is at zero for only, is at the edge of a cycle for only one of them. And all the rest are at different points. If you have staggered oscillators, okay, then you need to keep track of where each one is in its phase when you start your stopwatch. Only one of them could possibly be, or one set of them could possibly be at the amplitude position when your stopwatch is at zero. So the purpose of this whole phi thing is dealing with multiple oscillators. And here's my big punchline. Here's the big spoiler alert, is that you might think, or I might have thought, well, multiple oscillators, really? Are we dealing with that crap in this course? Like, really? A whole bunch of oscillators? Like, why would we ever? The answer is yes. The real punchline of Lab 3, the real purpose of Lab 3, by the time you get to the end or you do all the analysis and yada, yada, what you're trying to see at the end of Lab 3 is that what a wave motion is a collection, is a multiplicity of oscillators staggered in phase. Okay, I just gave away like a major punchline, and it is like it's usually like a big question on one of the exams. I'm going to say it again. I'm not writing it down because I'm not trying to confuse anybody, but your long-term objective in doing Lab 3 is what you're ultimately trying to see is that what a wave is, what wave motion is a whole bunch of harmonic oscillators doing their thing at the same time and in a related space, but all at different phases. Okay, that is the point. I'm gonna say this one other way. I'm not saying, and this confuses people a lot. We are studying simple harmonic oscillation this intensely because it is the key ingredient to wave motion. Where we're going with all of this is wave motion. Wave motion is the purpose of Lab 3. Wave motion is the purpose of sort of like a lot of the rest of the course for a while. What we care about is wave motion. I'm trying to help you, not confuse you, when I say harmonic oscillation itself is not wave motion. One thing going back and forth, that's not a wave. That's an oscillator. What we've been studying so far is oscillators. What you're seeing in Lab 3, what we're about to see, is that if you put together a bunch of oscillators together in a very specific way, if you stagger them all in phase, you will get a wave. So I'm saying you can't have wave motions without a lot of harmonic oscillations. Wave motions are built from oscillations. That's the key takeaway of Lab 3. But don't get ahead of yourself. The reason we have to go in this order is we're not saying that all oscillations are waves. And like all rectangles are squares, but not all squares are rectangles. All waves are made from multiple oscillators. What we've been studying so far is one oscillator at a time. Once you recognize that an oscillator can be put at a different phase, then you can put a bunch of oscillators together and create a wave, which is what's happening in Lab 3. In Lab 3, you're going backwards. You're seeing a wave and you're decomposing it and seeing how it really is simultaneously harmonic oscillations in time while it is also harmonic oscillations in space. Okay, that hopefully that may have helped. I don't know. That's just a big picture of what's going on in Lab 3 and how it relates to this. Okay, and if you have questions, please put them in the chat. But that was just like now I'm going to go back to homework 2 and just keep doing the math. Because I'm sure you've seen in Thursday when you sit down to do, excuse me, the analysis of Lab 3, it's a lot of taking derivatives and looking at these differential equations. You're ultimately going to get a new differential equation in your analysis of Thursday, but you can only understand it or be okay with it if you've practiced with this first one for a while first. So I'm going back to this one now. I hope that made any sense. Let me know. Oh, sorry. I'm looking at the chat. Oh, what was on the bottom of the previous page? Oh, sorry. Okay. The bottom of the previous page. But yeah, it would certainly not shock me if there were questions. It says, oh yeah, God, that is axe murdery handwriting. It says, yeah, what it's trying to say is that what it says we start the stopwatch 1/4 of a cycle in. That's like not even English. We start. It means what I'm trying to say is that when phi is pi over 2 radians, when you have a plus pi over 2 in that parentheses, what that really means is we waited until the thing had already covered a quarter of a cycle, and then we started our stopwatch. Why do I say a quarter of a cycle? Because if you just look at this math and check it out, if phi is pi over 2, that means that when t is 0, x is not x naught, but rather 0. It means that the thing is at the 0th position. It's at the equilibrium position when we start our stopwatch. If phi is pi over 2. Pi over 2 means quarter of a cycle. So a phi of pi over 2 means a delay or a head start in timing of a quarter of a cycle, which means the thing was already a quarter of a cycle into its motion when we started our stopwatch. And I'm assuming again, or I'm believing, here's an amplitude position, like 15 centimeters from equilibrium, for example. That's an amplitude. So to do a full cycle would mean to go all the way to negative amplitude and all the way back. A full cycle means all the way there to the other side and all the way back. That's a full cycle. So therefore, to me, that would be 2 pi radians. Therefore, to me, pi radians would be going all the way there. And so pi radians means a half a cycle. So if the phase constant, if phi were equal to pi, that would mean I started my stopwatch over there rather than over here. But if phi is pi over 2, it means I started my stopwatch when the mass was in the middle at x equals 0, like not positive x naught, not negative x naught, but 0. So it means I started my stopwatch when the mass was actually at equilibrium, i.e. a quarter of a cycle in. I'm glad I know someone was just asking about my handwriting, and I know that person got the point the minute I just maybe sort of translate the handwriting. But does that, oh, okay, good. Okay, I was just going to say, so does that make sense? And they said yes. Okay, cool. All right. So hopefully that made any sense. So that's the takeaway. That stupid question about 3.5 in the homework, I don't care about 3.5, but I'm saying from now on, we believe in this idea of a phase constant. It's like part of our solution to the differential equation for simple harmonic oscillation. Like that's the takeaway from now. So now I'm going to go to the next question in the homework, unless anybody wants to ask anything, which they certainly can. Hold on, I'm going to switch screen. I'm going to find the homework. So ooh, hello. First, I'm going to talk to myself for a while because that's socially acceptable. Okay. So now I'm going to, okay, something kind of different. All right. So now we're on I. So this is homework 2 continued. Homework 2 continued. So this is 1, derivatives. All right, I'm going to try an experiment here. I have so much that I could say about this, but I'm going to try first, just to do the answer and see what you think. Please ask me questions. If you want to ask, why are we doing this, or what does this mean, or what does it have to do with anything, please do. But for the moment, I'm just going to skip that and just do it. So it says, is x equals e to the negative t a solution? To our good friend, this. Okay, so it seems like we're shifting gears to the left. We're saying suddenly here's a completely different function that we haven't considered yet. Could this function describe simple harmonic oscillation? That's the question. Well, if I'm doing a GDP, okay, so all of a sudden we're talking about e to the, where did that come from in this physics class? It came from the fact that we're looking for functions that when you differentiate them twice, you get back themselves times a negative sign times a constant. That's what we're looking for, right? Like that's cosine is an example of that. You differentiate it once, you get negative sign. You differentiate again, you get negative cosine, right? So cosine has that character of satisfying the differential relationship that we're looking for. We're looking for functions that when you differentiate them twice, you get back themselves, but times a constant, which could be 1, times a negative. So it's suddenly, and we just noticed, okay, so I'm doing it. I'm already explaining this, which I said I wasn't going to do, but we just noticed that just when we thought we had the answer, like Z equals Z naught cosine omega t, like that described simple harmonic oscillator. It got us the answer to question 9 of homework 1B. So we thought we were done, or I thought we were done. But then it turned out, wait a minute, that was a answer, but it wasn't the only answer. Like it turns out, if you stick a number into the cosine argument, you get other things that you also get something that describes a simple harmonic oscillator. You also get something that satisfies the differential equation. And when you stick that number in and it still satisfies the differential equation, what we just found out is it has physical meaning. It wasn't just a math game, right? So now, because of that discovery, we're backing up and we're saying, wait, are there other mathematical functions that like do this thing? And if so, would they expand our understanding of the physics? That's what's happening now. And we think to ourselves, well, I know at least another function that when you differentiate it, you seem to get back itself, even if you differentiate it twice. Like in other words, what I think I know from a math class or from a calculus class is if I had in general, so I'm getting general now, right? I'm in step 3 GDP. I'm turning into Y's and X's now, just to make a math point. In general, if I have Y equals e to the X, then I know the derivative of that dy dx equals, I'm just asserting e to the X itself, right? Like, again, I'm just asserting that I'm believing that you know that from math. It's like a whole deep, fascinating discussion why that's true or what that means. But I'll say that literally that is the meaning of the exponential function. When people in real life or in the New York Times or something say, oh my God, it increases exponentially. Like often they just mean it increases a lot. Like, but if they're saying it seriously, when in life someone actually says, oh my God, it's like increasing exponentially, what they mean is something is increasing in a feedbacky kind of way. Right? They mean like when they say the interest compounds exponentially in your bank account, they mean that the amount of money that you get every day is not just a fixed number, that the amount that you have every day is based on how much you got, but how much you got is based on how much you have. So it builds on itself. That's what right? So exponential is the classic, the root function, the quintessential function that captures that idea of feedback. The derivative of the exponential function is literally itself. That's the exponential function is that function whose rate of change is itself. Okay, so I think you know that from math. So that's why we're trying it now. Like, so can we use that to describe harmonic oscillation? Because there's this feedback thing that we're trying to capture. So we try. So we write that down as our GDP. Now we're still going to use chain rule. Like this is still a composite function that we're looking at. So we still have chain rule. So I'm just writing it down to our minus. And if z equals a function of y, just in general, and y equals a function of x, then, dz dx equals dz dy times dy, right? We've already established that, but that's the chain rule. The derivative of the outer times the derivative of the inner equals the derivative of the whole thing. So that said, it seems to me that I can take derivatives now as per the problem. I could say, okay, so then, so I'm in step 4 now, in effect. Step 4, sorry, I skipped step 1 and 2, but I did. Step 4, PAW, so here, let me also change the screen. Sorry. I'm just looking at and again, feel free to interrupt in the chat at any time. Okay. Here, so now I'm back to the particularities of the problem. So I'm talking X and T now rather than Y and X. So here, I forget what we said. Actually, we said, X equals E to the negative, to the negative omega t. That was the given function. Therefore, I'm going to take, so to answer their question, I'm cutting to the chase. They say, does it satisfy the differential equation? No way of knowing unless I take two derivatives, exactly two derivatives. So here we go. So the first derivative, if I use my knowledge of exponential functions and I use the chain rule, I think you would agree with me that I would get this. I mean, stop me if you don't. Or again, you could stop me privately. It's the one post-COVID advantage we have in education. You can stop me privately. And then, of course, I'll find 85 ways to not use your name and still single you out and make you feel all embarrassed because apparently that's how I roll. Okay, so that's the first derivative, right? It's chain rule. Then the second derivative, I do that thing again. So I bring back the omega, I bring down the negative omega again. So a negative times a negative is a positive. So I get positive omega squared e to the negative 2 the omega t. I'm looking at the chat. I'm seeing, I'm assuming you're with me. Okay. So then does this? So the question is, now that's looking good. That's looking like something. But the question was, does this satisfy or solve? Does it satisfy this? Right? That's that. And notice that thing that we're trying to satisfy is still the same. We're trying different functions, but we're trying different functions to see if they satisfy the one differential equation that we have on the table right now. Why do we have one, or where is it? Because this is a physics class. The one differential equation we have on the table is the one that seems to describe this very important physical system known as a harmonic oscillator. So there's the differential equation. The question is, if we take two derivatives, do we get that? Well, the good news is, just like before, this whole thing here, e to the negative t, yeah, I mean, this whole thing is x. So we can substitute x in. That's the good news. We did get, when we took two derivatives of x, of this particular x, we did get x back. But however, if you're with me, it's close but no cigar, because we got x back times positive omega squared, not negative omega squared. Like, in other words, bad. Or in other words, no. Like, bottom line, I'll go back. Well, I'm going to go to the next, see if Peter's paying attention. You could tell me to go back to the next page. It would make me feel like you're paying attention. In fact, if you did, but I'm saying what we just learned is if x equals negative omega t, then d2x dt squared does not equal negative omega squared x. It equals positive omega squared x. Whoops. Which is not the same thing. Like +1 does not equal -1. Duh. I.e. x equals what we just showed, demonstrated, is that if you're trying to capture the motion of a simple harmonic oscillator, you're trying to see where is it as a function of time, what we just showed mathematically is you can use a cosine function to describe that, but you can't use an exponential function, so far it seems. And if you just step back and think about this, okay, in a way, you might be so not surprised that you might even wonder why we just spend time doing that. Like, if you know that cosine functions look like this, like they wiggle back and forth and back and forth, they cycle. Cosine functions are periodic. Hello. Cosine functions and sine functions are periodic. They're cyclical. Exponential functions are not. or at least raw exponential functions like this, they just go up or they go down monotonically forever. So in a way, it makes sense. Like you might say, well, yeah, like I would never think that you could describe an oscillator. Like how could you take the data from an oscillator through log or pro, put it on a graph and expect to find something that looks like this? You wouldn't. You would expect to find something that goes like this, right? So in some ways, this is just mathematical verification of something that you might have already been able to picture. Like, and so then again, you might say, but then why did we even try? Why, who would ever think that an exponential function would work? Like, why would we think that? I wouldn't think that. And good point. But we would think that maybe we tested it because exponential functions, when you differentiate them a couple of times, you do get back to themselves. Just the problem is just not with the negative sign. And the negative sign is key. The negative, this is reinforcing that that negative sign in the differential equation is necessary. That negative sign in the differential equation is the negative sign from Hooke's law. The negative sign is the thing that says we're always trying to go back to the center. If we're on the right, we're pulled to the left. If we're on the left, we're pulled to the right. That's what the negative sign says. That's what produces the cosine. If no negative sign, then you just get, okay. So far we're just saying that's the answer to the math question. See, I'm doing it. I'm like over. That's the answer to the math question. E function would not work. Then you might, and I'm not going to do this, you might say, okay, but was our problem, like maybe the problem is that we stuck in that negative sign into the argument in the first place. Like, why did we do that? Good point. But if you try, well, because I think we were hoping to get a negative sign. If you try, I'm not going to write this down, but if you try x equals e, well, I'll write it, I won't do it, nor x equals e to the just omega t, if you just try that, same problem is going to happen. You're going to take one derivative and get omega e omega t. Then you're going to take another derivative and get omega squared e omega. Like you won't get a negative sign at all. So you still have the same problem. So it seems like exponentials cannot describe cyclical functions. But weirdly then, and this is like a weird thing, I'll try not to over talk this. If we then go on in the homework, if we go to J, it now says, what about, oh, I'm in the, in J, it now says, remember, it says, even though there's no I in team, there is an I like in math. It says, let I be the square root of -1. And you think, wait, are we getting into imaginary numbers now? Yes, except that imaginary is a terrible name. They're not any more imaginary than any numbers are. I mean, complex is a better thing to call them. We are, and then if you're thinking, do I have to remember like all bunch of things about complex numbers? No. The one thing you have to know about complex numbers is that the whole basis of the system of complex numbers is defining I to name of whatever number would, when squared, get -1, right? Where's this coming from out of nowhere? Like, why is this? Because we have exactly this issue right now. Like we want to get a negative sign in the solution. We want to take two derivatives and produce a negative sign there. Each time we take derivative, we do chain rule and we bring down the omega. We want to multiply an omega by itself and somehow produce a negative sign. So it's like saying with regular numbers, wait, square root means like the square root of a number is the number which, when you multiply by itself, you get whatever I'm looking for. So when you're dealing with positive numbers, that's easy. Like a positive times a positive equals a positive, and also a negative times a negative equals a positive. So like the square root of 9, you could say is 3 or -3. Either one, if you square them, you get 9. But what if you want to get the square root of -9? Like what multiplied by itself will give you a negative number? The answer is I think the answer is whatever you give it any name you want, whatever it is that multiplied by itself gets -1. If we use that, even if you didn't, so I'm saying, let I be the name for whatever it is that when you multiply it by itself, you get -1 rather than +1. Then, if that's true, if that's true, that I stands for the square root of -1, something you might remember from math, but you don't have to memorize, logically, then okay, I to the first power equals the square root of -1. I to the second power equals I times I, right? Which means -1 times, square root of -1 times square root of -1. In other words, -1, right? If I is square root of -1, then by definition, I squared is -1. And yes, good. Wait, did I say that right? Yes, I totally agree. Very good direct chat person. I think we're in agreement, right? Yeah, someone in the direct chat just said the I squared is -1. Yes, I totally agree. Good. And therefore I cubed, like I'm not saying you would have memorized this, but you can just logically use the definition and say I cubed would be I times I squared. So that would be I times -1. In other words, negative I, right? And then, oh, good. Close. Okay, so someone's in the, all right, awesome. Someone's in the chat now saying, and I'm glad you're with me. Someone said, would that be +1? You're just one step ahead of me is all, because what would be like I to the cubed would not be +1. I to the cubed would be negative I, but certainly I to the fourth. I think that's what the person's thinking. I to the fourth would be I to the second times I to the second, and that would be -1 times -1. So that would be +1. I think that's what, right? Now, why am I writing this? So I'm saying, it didn't ask me any of this, but no, cool. No, you, and all of you, wait a minute. Good question. Also in the direct chat. So you guys are really totally with me. Wait. No, the uppercases are fine. I like uppercase. Wait, no, someone's asking in the chat, is this true for every problem or just this one? That's a really good question. I think I know what you mean. What I'm saying about I right here is always true from now on. It's always true. It's not just true for this problem. Is it always helpful or always relevant? No, probably not. Like often it's not needed at all. Like up until now, we didn't need to think about this. And we're not always going to need to think about this. You'll see in a minute when we need to think about it. So it's not, if you're asking that nervously, like, wait, do I suddenly have to learn this now? You do have to learn this, but just to this extent. All you have to see that I'm saying is if from here on in, I is the name for the square root of -1, then it follows that I to the first power, I to the second power, I to the third power, and I to the fourth power are these things. In fact, I'm going to go one step further. So I to the fifth power would be I to the fourth times I to the first, which would mean 1 times I. So notice I to the fifth cycles back to I. And then it keeps cycling. So it cycles in stages of 4, if you see what I mean. Like it takes 4 turns to get back to itself. Now that's a hint as to why this is even coming up now. If you're thinking, wait, suddenly I have to know about imaginary, like what? Well, first of all, I'm not saying you have to know any more than this. But second of all, yes, you do need to know this because apparently it really is bad to call these numbers imaginary. I mean, they're in your imagination as much as any numbers are. But just like all numbers, apparently we're about to see these can and should be used to describe things that actually happen in physical systems in space and time. What I mean is this. So I don't know if that's helping the person but here's what I mean. So this is true, what I just wrote down. And it all just follows directly from the definition that I from now on means square root of -1, right? Oh, okay, good. Oh, thank you, direct chat person. Awesome, because I was actually worried. Okay, good. So what am I going to do with this? Here's what I'm going to do. Then, given the above, hold on, I'm looking at how the question's phrased. Right. Then suddenly it says, let's try this weird function. Let's try x equals e to the I omega t. Now, yeah, so I'm going to take derivatives of that. Just note, it looks totally out of note, like, right? If we didn't just, it looks like, what? You're now asking about exponentials of complex, like what? we're just trying to build mathematical functions that might do the thing that we want them to do, which is survive with a negative sign after two time derivatives, right? We're looking for mathematical expressions that do that mathematical thing, because if they do, then that means they would be a way to analyze and predict the data, the space-time data for any physical harmonic oscillator. Like, we're looking for math to describe harmonic oscillators, which also, by the way, sidebar, more and more you might be seeing in physics, like in lab 1, but then especially in lab 2, and now especially in lab 3, more and more what we're trying to show you in physics is that what physics is really about, it's not really about taking equations and using equations to solve physics problems. It's not really about using equations to solve physics experiments. It's about doing physics experiments to generate to generate mathematical equations that describe the physical world. Right? So we're looking for mathematical functions that describe the data that we're getting from the physical world. That's what's happening here, specifically for the harmonic oscillator. So wait, I'm looking at the chat. Oh, boom. All right, someone is saying something in the chat. There's one person that is awesome. And I'm going to repeat. Well, I guess I'll repeat right now. But I'm going to repeat it again in a minute. Someone is saying, and definitely, like, way to go, you person, you. And wait, someone else is asking me to go back a page. Sorry, that's also awesome. Okay, I went back a page. But someone is noting that I seems to be kind of cyclical, kind of like cosine. So that maybe it does help for simple harmonic oscillation. Like, very, very good point. And and I'll repeat that or expand on that in a minute when we do the math. But yes, like, the issue is simple harmonic oscillation is cyclical motion. We're trying to come up with math that describes cyclical motion. Cosine does, and it seemed like for a minute exponentials did not. But now it seems like I kind of does have some sort of cyclical quality to it. So now we're almost like guessing that maybe if you put I together with an exponential, like, maybe we'll have something. And that's what someone in the chat is saying. She or he is saying that I is also cyclical, kind of like cosine. So that's cool. Yeah, okay. So very cool. And then the other person saying, thank you. So let's see. If we take the derivative, take one derivative, and you might say, wait, take derivative of, okay, I keep talking. And please, even if you're thinking, wait, I've never taken the derivative of a complex exponential before. Well, you haven't? What kind of parties do you go to? No, if you're thinking, I've never taken the derivative of a complex exponential before, what I'm here to say is it's nothing new. I mean, if you have the chain rule and you know what to do with two exponentials, you know what to do, because I is an interesting kind of number, but it's just a number. It's just a constant. I is a constant. So we're going to treat this derivative the way we treat all derivatives. Like, the I in there is a constant, just like omega is a constant. So if I take one derivative, I'm going to get I omega e to the I omega t, right? Chain rule. And then if I take another derivative, I'm going to bring down the I omega again. So I'll get I squared omega squared. And you have to say it in that accent, E I omega t, right? And that looks like, what is that? But now we recall what we just noted a couple. Wait, hold on. Wait, I'm about to get, great thing in the chat. Minor rebuttal. Let's replay. Hang that thought for, great thought. Hold on for a second. I will address that. But just to wrap up this point, we have I squared omega squared e to the I omega t, and that looks like a bunch of nonsense. But remember, I squared is -1. We just established, because I is square root of -1. So apparently, well, I'll go to the next page. Apparently, tell me if you want me to go back a page, but evidently, if x equals an exponential by itself to a positive or a negative, it doesn't work. But if x equals an exponential raised to a complex power, whoa, like I omega t, and if you check it, you'll see, it doesn't matter if it's positive or negative I omega t, then then it does work. So then evidently, complex exponentials are a way to describe the physical world of simple harmonic oscillators, as surprising as it may be. It's something about sticking an imaginary number, into an exponential function evidently gives it the cyclical character of a cosine function. That actually turns out to be a very deep and powerful, important result of math itself. Like it's called Euler's equivalence. The idea that you can write, I mean, it turns out, it turns out that you can say e to the I omega equals cosine omega plus I sine omega. Like you can express cosines with complex exponentials and vice versa. You can express exponentials with complex cosines, etc. And which is mathematically interesting. But physically, what we're saying is there is physical meaning to complex numbers. If you put a complex number is a way of imbuing an exponential function with cyclical character. On Katie's very, very fair and awesome and thoughtful minor rebuttal, I think I have I love it, but I think that I rebuttal the rebuttal. Like put it this way, I think the cycle is 4 steps either way. Oh yeah, sorry, yeah. I think the cycle is 4 steps either way. Put it this way. And I almost want to write this down. I might write this down, but I might not, because it might, I don't know, you tell me if you want me to. But like, if the function is sine of if y is sine of x, we take one derivative. If the function is y equals sine of x, you take one derivative, you get cosine of x. You take another derivative, you get negative sine of x. You take another, whoa, okay. You take another derivative, you get negative. Now I've lost. If you have sine of x, you take one derivative, you get cosine of x. You take another derivative, you get negative sine of x. You take another derivative, you get negative cosine of x. You take another derivative and you get sine of x, right? If you do it 4 times, if you take 4 derivatives, you get back to what you started, sine of x. And with I think I to the 0th is 1, I to the 1 is I to the 2 is negative 1, I to the 3 is negative I to the 4 is 1. I think I just did that, right? I think it's, oh, fair enough. Okay, cool. And I appreciate I appreciate the honesty and but yes, and it always confuses me too. It's always about like whether you count the 0th stage or not. What? Hello? Okay. So yeah. So it's actually a staggering coincidence that I cycles in stages of 4, just like cosine or whatever starts cycles in stages of 4. And of course, e to the x, because it cycles in stages of 1, of course it does land on 4 as well, if that makes any sense. Like if you do 4 cycles of e to the x, of course you end up back with e to the x, because e to the x, e to the x, e to the x, e to the x. So all 3 of them are intertwined in this kind of function, which is called an Euler function. And it can be, bottom line, from here on in, when we describe simple harmonic oscillators, we can describe them with cosines, or we can describe them with complex exponentials. And it turns out in higher and higher levels of physics, especially in circuits and stuff like that, it turns out to be much more convenient and useful to describe this kind of physical phenomenon with a complex exponential rather than with a cosine. Same graph, same data, but if nothing else, I'm saying complex numbers are just as physical as any other numbers. Okay, we have 6 minutes. So okay, now, what do you need to know for the exam? Or what do you need to know for labs? Or like, how does that relate? This is back to one of the, cool. Oh my God. Back to someone who was in the direct chat and definitely asked, like, wait, what, like, just to be clear, you need to know what I just said. And there's usually a question on on the midterm exam or something that makes you show that you know how exponentials and complexes work, like this. Like you'll need to know a question like this. But then just to be clear, from here on in the labs, and where we're building waves from this stuff, generally in this class, we're still going to use the cosine. We're not going to go very far, any farther than this. With the complex exponentials, just to be honest and clear, now that we've seen that, we'll go back to cosines and sines and use those. So don't get, so this is a little bit of a just a cool highlight. Don't, if it didn't really land with you, don't get too worried about it. But I hopefully for some people it kind of just excites you to, it excites me to show me that there's more of a relationship between abstract math and real physics than I would have known. But that said, and we have 4 minutes, I'm gonna go on. I know we only have 4 minutes. I want to do, sorry, see if I can just do one more example just to get us back on track for the waves. Oh yeah. All right, let's before I think this now, these two things, these cosine functions, again, they are sort of trying to practice, they're trying to get you to see how the phases work for the purpose of the wave stuff. So you know what I'm going to just do right now with 4 minutes? I'm going to literally write down the answers to these right now. I'm going to give you the answer. I'm going to try to not talk at all. I'm just going to write down the answers so you can check your answers and see if you have any questions about it, which you can raise right at the beginning of class, next class. Okay. But here's just to wrap this up. And again, so that, in lab 3, what you're trying to see with all the logger pro and everything, you're trying to see that if you hold X fixed, if you look at one position on your rope and you measure height as a function of time, then you get cosine functions like these. But also at the same time, if you pick one moment of time, one snapshot, and you measure height as a function of X, you similarly get these same cosine functions. What you're trying to see in lab 3 is that a wave consists of cosine harmonic oscillations in time at the same time as harmonic oscillations in space. What you're trying to see in lab 3 is that these cosine functions work exactly like this, both for time and for space when you have a wave. Right now, at the stage in the homework, we're not at a wave. These are just individual oscillators. But a wave is a combination, a composition of cosine functions. That's why we're obsessing over it. Okay, so I'm just gonna, we have 3 minutes now, 2 minutes. I'm just gonna write down answers. Oh wait, okay. Oh wait, people have to, okay. Well, if you have to go. I'm gonna just try to write down some of these answers right now for the sake of anybody who. Sorry, I got myself all. Okay. can't be right. Sorry. Yeah, wait, I guess people have to run. Wait, you know what? We're going to stop right. Don't write that one down. We'll pick up on that tomorrow. We'll just leave it at that for the moment. Okay, so we'll pick up on that on Wednesday and the lab. If you come with questions about the lab on Wednesday. Okay. Sorry. I just love, have a great day. Yes, yes, thank you. Yes, have a good day. Sorry. But I'm here in case anybody has questions. Goodbye.